Let's try to solve a problem that exemplifies how the instant Gibbs free energy depends on the concentration. This problem is related to the glycolysis pathway that you have learned in physiology or biochemistry. Uh, the pathway of glycolysis, if you read what's written here, it goes from, you start from glucose, and well, OH. So all cells in your body can undergo this pathway in which glucose becomes glucose 6 phosphate, and then all the way to 2 molecules of pyruvate. And pyruvate, let me make sure I can write pyruvate. There is a molecule of pyruvate. So this is a very standard biochemical pathway. All cells can catabolize glucose to obtain 2 molecules of ATP, as you have learned in your biology classes. And what we have here is a table with the standard Gibbs free energy. And this tells you already which of the reactions, the more negative your reaction is, the more product bound, at least in principle, your reaction is. However, as you can see in this equation, if you change the concentrations, in this case in the cytoplasm of the cell, that's where glycolysis pathway takes place, you can change the actual spontaneity, the actual direction of that specific reaction. So if you see in this column the instant Gibbs free energy, this one is more negative. How can the cell make this first reaction that was already negative, make it more negative? Well, if you decrease the value of Q, in other words, if you have a lot of reactants and you have not a lot of products, that's when you're going to have a small number of Q that will make, if this is very small, logarithm of something smaller than 1 will be negative, and that will decrease your delta G. So what matters in the cell is this column over here, the instant Gibbs free energy, because the cell can play with the concentrations of reactants and products of all these 10 steps for the catabolism of glucose to move a reaction forward or keep it not moving very forward. So that will strongly depend on the conditions of the cell. Typically, the reactions that are very exergonic are target for regulation and therefore for drugs and so on. So the more negative these numbers are, it means that if you can cut that enzyme catabolizing that specific step, it will be a target for regulation and for drugs, etc. So in this column what you see is just the difference. So in an Excel spreadsheet you just subtract this column from this column, and this tells you a little bit how much we have changed the concentrations with respect to the 1 molar that the standard conditions would be. So let's try to answer some questions about this 10-step glycolysis pathway. We're being asked, in here we have 4 questions, so we're being asked the step with the largest equilibrium constant. Let me remind you that there is a relationship between the equilibrium constant and the standard Gibbs free energy. This just tells you that the larger the K, okay, the logarithm of something large is positive, negative, the more negative will be your delta G standard. Notice that it's a standard one. So let's see what step contains the most negative one. Clearly, step 10 is the most negative change in Gibbs free energy standard. So step 10 is the one that would have the equilibrium constant largest. Notice that in the cell, however, to keep things moving, none of the reactions are in equilibrium, and this is why the cell can afford to keep concentrations outside of equilibrium, so that it's in its own interest. So now let's list all the product favor reactions at cell conditions. At cell conditions, your delta G, the delta G non-standard, has to be negative. The delta G non-standard has to be negative. So we do not care if the Gibbs free energy standard is positive or negative. At cell conditions, the cell has changed the concentrations of reactants and products in so many different ways through many regulation pathways. We are interested in seeing which of the steps will have a negative standard, a negative instant Gibbs free energy. So let's go back here. Definitely step 1, step 2, step 3, 4, this one 2, this one 2. So all but 5, 7, and 8. Whoops. So all but 5, 7, and 8. The rest are to more or less extent product bound. They are product favored reactions. Now let's get a little bit trickier here. What is the step with the largest highest ratio? It's asking, so the higher the ratio, the larger the Q. So it's asking which of the step has in the cell the largest Q. So again, the cell can, through different indirect ways, control the concentrations of different metabolites in the cytoplasm or in any other place in the cell. Therefore, we're being asked what is the step with the highest Q. So if we use this equation again, well, we'll see that delta G is delta G0. This is equal to RT logarithm of Q. So Q is delta G negative delta G0 over RT. So how can I get a large Q? Well, when I have a large and positive exponent. Does that make sense? So if I have a large and positive exponent, I will have a large Q. So which one? Notice that I already have this up here. So I'm looking for all have the same R and the same temperature. So the largest exponent will be the most positive of these. So by far, step 7 is the largest. So notice that it was in principle a fairly product favored reaction, actually the second most favored reaction, but the cell has put so many products in the cytoplasm that has converted what in the standard conditions would be a product favored reaction, a reactant favored reaction. Now this is positive, okay, and that can be exemplified here. So step 7 will have the largest Q. So step 7, if you will, is the one in which the cell has done its highest effect to reverse that reaction. And now, so what is the step with the smallest ratio? Again, we're being asked a small q, and a small q, as we have discussed before, that's because there is not enough products. So we can still apply this equation here. We are looking for the, if you will, the most negative or the smallest of this subtraction. This was the largest, and I'm seeing, I think, yep, the step 4, it was fairly reactant favored, very positive, so fairly reactant favored, an equilibrium constant that is very small, and yet in cell conditions, by changing Q, by adding a lot of reactants and subtracting a lot of products, it has made the reaction more product favored. So step 4 will be the one that has the smallest ratio. Hopefully this makes some sense. One would just need to plug in numbers to actually find the actual value for Q, and if you're given the molarity of products and reactants, we could actually calculate delta G, etc., etc. Okay, this was a qualitative discussion, or semi-qualitative, because we actually had to manipulate some numbers, but hopefully you shouldn't have too much of a trouble when you are being asked with specific numbers for Q or for concentrations of reactants and products. This is the star equation of this whole problem, and I hope that you can see with the application in living system the extent of thermodynamics. It's actually applicable to many areas, and living systems is one of them.